next speaker. And we have today here the pleasure to have Dr. Margaret Dominguez. She is an optical engineer at NASA Goddard Space Flight Center, and she's also a researcher associated to a National Institute of Standard and Technology. So with that being said, Dr. Margaret, so you can start.
So thank you, Larry, for that introduction and for the invitation. So just to make it a little funky, I named my presentation From a Pig Farm to the Stars, My Journey to NASA, and we'll talk a little bit about what I do at NASA. I like to talk of my life in terms of crossing bridges. So I'm originally from Mexico, and I grew up in a pig farm, and I studied physics at the Universidad de las Américas Puebla in Mexico. And then when I finished my physics undergrad, I wanted to continue to advance my education. So I decided to cross a pretty big bridge and move out of Mexico and go to the College of Optical Sciences at the University of Arizona to study the dual master's PhD program. And I was successfully able to finish that a few years ago. But during my time there, I was very involved with the Women in Optics group at the College of Optical Sciences. So there I am at an elementary school doing some optics demonstrations with some students. This was my research group at the College of Optical Sciences, an international community that we were all part of, a wonderful program. During my time there, I was able to travel to different places. So here I am attending a conference in Berlin, where I was able to present a poster of the research that I was doing at that time. So that was really exciting. And then, formerly OSA and now Optica, I was able to compete in an international competition for optics kits. So we made like a shoebox size combination of optics demonstrations, and we were able to compete like 25 different universities from all over the world. Who had the most creative optics demonstrations that were cheap, sort of like easy to get access to, and that, you weren't concerned if a child would drop it or they'd break, because they would be really easily accessible. And it was a wonderful opportunity. So I've sort of always been involved with a little bit of outreach and love to travel and do optics whenever possible. Then after I finished my master's and PhD at the University of Arizona, I moved and I crossed another bridge, now leaving Arizona and moving across the US into Maryland, where I'm currently working at the NASA Goddard Space Flight Center, which is where I am now as I'm talking to you guys today. Now, at my time at NASA, I like to say that I wear two different hats. I'm an engineer and I'm an outreach person. And there's a really good word for this in Spanish, divulgadora. It doesn't quite translate the same in English, but I'd say I'm an outreach person. I've been so lucky that I've been able to travel to different places to give invited TED Talks at my alma mater. This is for another event called TEDx Mexico City Women. I was able to go to Peru, to the Pontificia Universidad Católica del Perú, to give a talk about the work I'm doing at Goddard. This is at a children's museum in Mexico City called Papalote Museo del Niño. So very, very popular children's museum in Mexico City. This was last year, actually, before the pandemic hit. I was invited to go to Madrid to a school, to an elementary school, and I gave a talk to 150 elementary schoolers, and I was very nervous because I thought they would be bored, but they were actually awesome, and they had wonderful questions when I was able to talk about the work that NASA's doing and what we know about our expanding universe. Of course, in person is not always possible, as we are connecting right now virtually, and even before the pandemic, we do as many virtual presentations as we can. So here I'm connecting with a planetarium in Cancun. And one of the highlights of my year last year in the middle of the pandemic was that I was invited to be one of three panelists, or one of the panelists was Jose Hernandez, a Mexican astronaut through NASA. So it was very exciting for me to sort of share the stage with him and talk about the work that we're doing at NASA. So that was really, really wonderful. I've been involved with different outreach programs that specifically focus on recruiting Latinas, middle school, elementary school age, into STEM, science, technology, engineering, and math. So two different efforts, Latina Sci Girls and Tecnolochicas, that have either invited me or nominated me and want to be part of this effort. where I'm doing constantly recruitment and just generally just sharing my passion for optics and hopefully spreading that passion to some of these girls that some of them are clearly eager to learn more and potentially go into fields like optics, right? Recruit future optics people into our field. But I love to do outreach so much. I really like to do this as much as possible. So I'm sneaking out so I can chat with you guys today. And I try to do this as much as I can in my free time and on the weekend that I actually married another optical engineer. And on our wedding day, we had an optics demo for all the wedding guests that we had. So I really have a passion for optics that I really want to share this, even on such a special day as my wedding day, that I told my husband we need to have an optics demo. So there you go. And obviously, that transcends that because now I'm so lucky that I was selected to be one of the Optica ambassadors for this year, 2021. So, the love for optics continues to spread and grow. And I'm so happy to be talking to you guys today about that. Okay, now let's switch topics a little bit. Let's get more serious. Let's talk about the work that I'm doing at NASA Goddard. So NASA has multiple locations distributed throughout the US, which you can sort of think about them as campuses. And I'm at the center that's called Goddard. We're located in Maryland. And at Goddard, we focus on 4 different science fields: earth science, astrophysics, heliophysics, and planetary science. I've always been focused on supporting missions with an astrophysics focus. But throughout the whole center, we focus on all of these areas of science. So earth science studies our planet, missions that monitor the earth, the water levels, and that look at fires and that look at weather patterns and things like that. So anything that is affecting our earth, we have a lot of satellites that are currently monitoring that. Astrophysics missions focus on studying the relationship of our planet within our solar system and beyond that. Heliophysics studies the sun and our relationship with the sun, and planetary sciences focus on studying other planets outside of solar system and maybe potentially looking for planets that could potentially have life similar to what exists in our planet. Here are a couple fun pictures to show you what my everyday looks like when I'm in the lab, even in the middle, still as we were recovering from the pandemic. This is what I do most of my time. I'll be in a bunny suit. Behind me in that picture on the right is a CMM, a coordinate measuring machine that has an accuracy of about 1 micron if we're using the optical probe, or submicron if, 1 micron if we're using the mechanical probe, so the touch probe that physically makes contact with surfaces. Or if we use the optical probe that is non-contact, is about submicron accuracy. I'm currently in the process of building the GRISM. In the picture on the left, you see one of the prototype versions of the GRISM, and I'm going to talk about what the GRISM is in just a minute. So I work with my colleagues to do optical testing. My area, my specialty is optical metrology. That was for my PhD, and that's what I continue to do at work. So I'll develop our plans and implement them to do optical testing on this instrument that's called the GRISM. I've been lucky enough to work in past years on the Hubble Space Telescope. We are getting so excited to prepare for the launch of the James Webb Space Telescope, which will be launched later this year in December, and that's going to be 1.5 million kilometers away from our planet. So we're really excited to launch this telescope that is really, really big, really cold, really far away, and I'm lucky that I was able to work on it. I'm currently working on the Roman Space Telescope. And this is a NASA observatory. It has a primary mirror of 2.4 meters in diameter. And we estimate that it will have about a 5-year lifetime mission. Hopefully we're able to extend that an extra 5 years. It will also be 1.5 million kilometers away from our planet. So at the same position where James Webb is going to be, but it's going to be about the size of Hubble. So it's sort of like a hybrid. Hubble is about the size of a bus. James Webb is about the size of a tennis court. So Roman will be as far as James Webb, but at the size of Hubble. There are 2 instruments that sit aboard the Roman Space Telescope, the Wide Field instrument and the coronagraph instrument. And I'm currently working on a component of the Wide Field instrument. So let's take a look of what this telescope looks like. So that's the outside of this telescope. If we were able to sort of strip the outside and look at the optical design, this is what we'd be able to see. So for those of you that are familiar with telescope designs, This is the primary mirror. So the light would come from the universe, from a distant star. The incident on the primary mirror, it would reflect from the primary onto the secondary. The primary has a hole in the center. So the light from the secondary would go through the hole, hit this flat, this flat. So just a fancy mirror that is essentially flat. And then they would hit it, the tertiary. In terms of, if you guys are familiar with optical design lingo, this is a TMA, a 3-mirror and a stigmat design. So 3-mirror, primary, secondary, tertiary. And the detector plane sits over here, but before the light hits the detector plane, it goes through this little guy that's called the grism. And that's what I'm currently, I just walked away from the lab. We're testing one of the parts that's going to go to space. That's part of this grism. At NASA, we build a lot of prototypes, so we make sure over and over and over again that we know how to do it and we can do it right, and we test our process and our approach. And then it's taken years of getting ready, and we're finally now working with the actual parts that are going to space. It's very exciting, a little nerve-wracking, but very exciting overall. I want to give you sort of like a zoomed in picture, more detail of the wide field instrument. So remember I showed you that primary, the secondary would be up here, these two fold flats, basically just flat mirrors, that tertiary mirror. And now you see the element wheel. This is this big element wheel. And one of the members of the element wheel is that grism. So that's the part that I'm working on building. And this is actually the prism, and I'm supporting that effort as well. So very, very exciting. And we don't have a lot of time. So, so let's talk about some of the lessons that I've learned throughout my professional development so far that I would like to share with you guys. Take a risk, be bold. In order for us to be able to advance, sometimes we need to take a risk and we need to speak up, always in a respectful and a professional way, but sort of having that confidence in ourselves that we can take a risk, that we can take it a step further is extremely, extremely important. So I know that can be challenging at times, but it's important for us to have that confidence in ourselves, to be bold, to speak up, especially if something is being done incorrectly. So at NASA, we have a very well-known understanding that at any level, it doesn't matter if you're a brand new, new employee, or you've been here for a long time, or if you're young or you're old, or any other factors. If you see something that you think is wrong, if you see something happening in the middle of a test, or we're handling something incorrectly, we're not being safe, it doesn't matter who you are, you can point it out and you will be heard. So it's important to sort of exercise that, paying attention and speaking up. Give back, right? None of us have so little that we can't share it with anybody else, even if that's just a few minutes of your time to listen to somebody else, to talk to somebody else about whatever that may be. It applies to your professional or personal lives as well. Never stop learning. We have so many people that are experts at NASA, and that's because they understand that things are changing still and they have to continue to educate themselves. You're never going to know everything, right? So the smartest people that I know are the people that understand that they have to continue to study. So I can understand after you just finish a PhD, you're like, I don't want to keep studying. But we do always have to be in that process. Continue to educate yourselves about what's happening and staying up to date. And something really, really important that I remind myself every day: document and communicate, and more specifically with an emphasis in knowledge transfer. So there can be a lot of really useful knowledge that you can learn something really good and you understand it really well, but let's accept that 5 years from now, maybe we won't remember what we learned anymore. So writing it down, communicating to the next person that's going to do it is extremely important. So to transfer that knowledge, whatever knowledge you have, if it just stays with you, it's not going to be very useful. So let's transfer that to somebody else. So exercising knowledge transfer, extremely important. And since we're talking about this event for women in optics, let me just throw some stats out there. They're not super good, but it gives us some perspective. And if we notice the trends, things are getting better. So of course, because I'm from Mexico, I have to throw this number out there. About 12% of all engineers in Mexico are women. In the US, you'd think the numbers would be a little higher, and they are, but just a little bit, only at 13%. Canada is doing a little bit better at 19%. And then we see Finland is doing even better, but still not quite where we wish. Japan is not doing as well as we thought either. So again, all these numbers are so on the lower end. This is a little bit of a surprising number for Costa Rica, where they're about at 31%. This is just to give us a picture of where we are. If we look at the trends for the past 50 years, we see that the numbers are going up. We definitely can engage that positive slope, but it's up to us. It's up to me, certainly. I tell myself to make sure that I'm working to continue to grow these numbers, right? So the recruitment, the communication, the reaching out is part of all our responsibilities. It's certainly part of my responsibility. So it's always good to just sort of keep these numbers in mind and do the best that we can to continue to enhance them. And I want to end with one of my favorite phrases from Mary Curie. Life is not easy for any of us, but what does it matter? We must be perseverant and, above all, have confidence in ourselves. Thank you so much, guys. Because you are in Puerto Rico, please follow NASA en Español through all of the different social media platforms, and feel free to follow me on Twitter and Instagram. Thank you so much for your time.
Thank you very much, Dr. Margaret. We really appreciate what you shared today, right? Or the knowledge that you have and all your path in your career, professional career. So let's see if we have a few questions and a Q&A. So if the attendants have any question, you can go to the Q&A panel and put there any question or any suggestion of if you want to hear something about. So please go there and you can do it now.
Yes, I have some questions. Well, only one question. First of all, thank you, Margaret, for that very brilliant presentation, and I know that all of us we enjoy a lot your presentation. Well, my question is regarding the Roman Space Telescope, which I've been trying. Well, I worked last year in designing a telescope as well,
Nice.
implementing some elliptical mirrors to a telescope, which is the primary object. It is a diffraction grating. And well, I know that these configurations enable to minimize the three main optical aberrations: spherical, coma, and astigmatism. What was the challenge that you have to suffer to design this system and constructing as well?
Well, so there are a number of challenges. So for the GRISM, the specific instrument that I've been working on for many years, and that's a great question, Diego. Thank you. We have to. There's so many things that go into the effort of sending something into space. We work with vendors for years to make sure that the vendor can make the part that we want, and sometimes the vendor thinks they understand the process really well, and something happens along the way, and something goes wrong. During the pandemic, we of course had some shortages. We needed the specific type of glass that we can send into space, and we couldn't get as much of it, right? So things like that are just logistical in nature that are happening. Getting instruments, adequate instrumentation, so interferometers. We had to buy 2 new infrared interferometers to be able to measure the optical performance of our system, because we want to make sure it's working properly before we send it to space. The prism, for instance, uses materials like calcium fluoride. Calcium fluoride is a glass that's really soft. So when you try to polish it into shape, it's very brittle, and it sort of leaves those polishing marks in the process. And that's going to affect, you're going to get some mid-frequency errors as you transmit. So when you're measuring the optical performance, you're going to see those issues. So there's lots of issues that can come into play. At NASA, we work on, we call them TRL, technology readiness levels. So whenever we send something to space, we want to make sure that whatever we're sending is technology ready really high. So we have levels from 1 to 6. So most of the stuff we send is level 5 or 6. And that means that we understand that we've sent it to space. We know how it's going to behave, and there's less surprises that can come up. That doesn't mean, however, that we don't sometimes send something new. So for instance, one of the other instruments on board Roman, the coronagraph instrument, that's a tech demo. So we're saying that instrument, we're sending it, and we're going to do our best for it to work well. If it doesn't, we said it was a demo, and it's okay. We're doing all that we can so that it works good. But sometimes that's not possible. And that's how we develop the technology to be ready so that we can use that in the future. So I don't know if that answered your question. There's so many things that go into making these telescopes. You're absolutely correct. When we focus on the design, the TMA, we're looking to reduce that coma, that astigmatism, all of these aberrations that contribute to getting good optical performance. It can never be zero, right? We have to start with some residual in the design and some residual in the manufacturing. But we sort of build our error budget so that we take into account all of these little errors, and we say we cannot be any worse than whatever that minimum range is. And we work really hard in the lab to adjust things as needed so that we hit that target. But of course, as any NASA mission, they're only possible through international collaboration and thousands of people everywhere in the world working together. And we actually have a lot of people that are from Universidad de Puerto Rico, Campo Mayagüez, that are at Goddard doing work, contributing to Roman and to many of the other missions that we have here.
Okay, thank you so much. And I have one more question. I know that, I understand that there is a lot of people working within a project, and I love instrumentation projects. And in this case, I know you have to take into account these biggest sizes of telescopes and so on. Did you use freeform surfaces or non-rotational symmetric surfaces?
That's
I
a
know
great
that.
question.
Yeah, they can decrease.
You can finish, I'm sorry.
Yes. I know that they can significantly decrease the performance for a fixed volume, which is the whole telescope as well. So probably we could decrease the 20% less volume of this whole construction using this type of surfaces. Or I don't know if it was used. And
That's a great question, Diego. And we are working currently on developing that technology. It's funny that you say that. I said my husband is also an optical engineer. He's a designer, so he's always designing telescopes, and he loves to put freeforms in there. And I'm a builder. I manufacture, install, assemble, align, and I always tell him, who's going to align and manufacture your freeform optic? It's so much harder than just to manufacture like an ellipse, a parabola, a sphere for sure. So we are not ready right now to send any freeform like in a telescope like this one. We have done freeform for like CubeSats, so missions that have like about a 2-year duration and they go around our planet. They're much closer and they're much shorter missions. And we are working on developing that freeform technology because, as you said, it's lighter, it's more efficient. So we definitely, whenever we send anything to space, it's really costly. And whatever amount of mass we're sending to space, it costs a lot more. So we want to keep it as light, as compact as we can. And freeform is definitely the future. So we're working on developing that technology to build that technology readiness level so that we can be using it in the future. Right now, it's not ready for us to be sending it on something like Roman or a James Webb. We're just using some conics, things that are a little bit more complex than just spherical surfaces, but not yet as complicated as a freeform. So we are working towards that, but a telescope like Roman won't have that yet. That's in the future. Great question, Diego. Thank you.
okay, thank you so much. Thanks.
Well, Margaret, thank you very much. We really appreciate your participation today with us. And